So I will be going over chapter 4.1 of the textbook, General Properties of Aqueous Solutions. I'm just gonna be going over like normal solutions and specifically electrolyte properties. So you probably already know this, but just an example, I'm adding salt or NaCl to this water, H2O. So the H2O is considered the solvent, and the NaCl is considered the solute. That is the terms that you'll be using throughout all of chemistry. The thing that is being added, or the thing that is in lower quantity, is always the solute, and the thing that is the larger example, like the water here, that is being mixed to have the salt in it, is the solvent. So what is an electrolytic solution? Well, and the textbook uses this solution too. I mean, this example. Um, you've been taught since you're a little baby and through media that you shouldn't put your toaster in your bathtub or else you'll die. And that's because we consider that as a general population that water is a conductor of electricity. That's a misconception though, because pure water itself is a very poor conductor of electricity because it does not ionize well. It ionizes a little bit, but not as much to be considered a good conductor. So the reason why tap water or just normal water that we handle on a daily basis is considered a good uh, conductor or considered an electrolytic solution generally is that they have ions in them. They have ionizable materials inside of the water so that ions can form in it. So the reason why ions are conductive is something that you'll get into later, but basically TLDR, the more ions you have, the easier electricity can move inside of your solution. More easily it can move around. Something to do with the electrons. You'll get into that. I don't really want to complicate this too much. So for example, with my NaCl and H2O example, when the NaCl goes in the water, it will break up into Na plus and Cl minus ions. So these ions are just going to be chilling, and when hit with electricity, it'll conduct it very easily. So there are other examples of this, like there's phosphates in your water, sometimes there's ammonia in your water, poison in your water, just stuff like that. Yeah. But generally, if not all the time, you'll be handling electrolytic solutions when you drink your water or when you do other stuff like that. So some examples of solutions that are not electrolytic are things that do not form ions. So like let's say you have pure water and then you add sucrose, C12, H22, O11. Now, if you add that to water, the sucrose is not going to break up. The sucrose is not going to form ions, therefore it will not conduct electricity. Therefore, a solution of pure water and sucrose is not considered an electrolyte. It's considered a non-electrolyte. And a solution containing pure water and NaCl, furthermore Na plus and Cl minus ions, that is considered an electrolytic solution. Now, these compounds such as NaCl or I don't know, KMNO4, these ionic compounds are the things that will dissolve in water, that will deprotonate in water, and form your electrolytic solutions. If you don't know what an ionic compound is, it's just when you have a non-metal and a metal in a bond. At least one metal. So yeah, that's all. Another example of an electrolytic solution is like when you have an acid, like you have HCl, a strong acid. Now this will deprotonate into H plus and Cl minus ions. That is also considered electrolytic, if not dangerous. So another thing to consider is that we have strong electrolytes and weak electrolytes. Strong electrolytes have solutes like NaCl or HCl that are completely dissolved into ions. Like if you put HCl into water, it's likely that almost, if not all of it, actually probably all of it, will become HCl ions, or H plus and Cl ions. Now, a weak electrolyte is one where a solution has solutes that only part of them deprotonate. For example, we have acetic acid. So this is kind of a long one. CH3COOH. And when we have weak electrolytes, some of it will go back into being in its base form. We'll get into that later in acid base. But that's how you kind of write that out. You don't have to worry about that yet. So here, in this reaction, we have the weak acid, acetic acid, dissolving or deprotonating into the base version of, I think it's acetate. Yeah, acetate and H plus ion. Now, not all of this acetic acid will become acetate and a and a H plus ion, but a large majority of it will, but not all of it. And that's something that's very important to consider. And we'll get into that when we get into the acid base unit. But that's kind of the basics.